fun. Okay, so the next question that we got on the menu today is asking us, a spring has a or a spring has a force constant of 147 newtons per meter and an unstretched length of 5 centimeters. On one end is of the spring, I'm guessing, is attached to a post that is free to rotate in the center of a smooth table, as shown in the top view diagram. The other end of the spring is attached to a 7-kilogram disc moving in a uniform circular motion on the table. And it stretches the internal string by 2 centimeters. There's no friction, so that's nice. So it's going to ask, the first question is asking us is, what is the centripetal force of the disc? Answer in newtons. And what is the work done on the disc by the spring doing one full circle? Okay, so let's go back to the question and extract our information of interest. Okay, so the first thing that we got going on is the spring has a force constant of 147 newtons per meter. Okay, so let's call that K. Typically, K is what you use to represent a spring constant. So let's call that Ks for constant spring. We don't use C because C is used for the speed of light as well for charge, so we don't want to be too confusing, so we use K. And we know that we have 147 newtons per meter. Okay, now we also have the unstretched length. Let's call that X0. Okay, so this is, let's actually write out what these are. So this is spring constant. And our unstretched length, 5 centimeters. So let's write that instead as 5 times, or instead 5 centimeters, which is equal to 0.05 meters. So this is unstretched length. Now it's good to convert all of your given numbers into base SI. It will make your calculations a lot easier. Otherwise, you need to deal with like the centi prefix and like milli prefixes. Those prefixes are uncomfortable to deal with, but you got to do what you got to do. So yeah, this is what I would recommend. And the stretched length is 7 centimeters. So let's call that XS or X. X long is 7 centimeters, and that is 0.07 meters stretched length. Length total. And for the change in X, this is going to be important because for when we do the force calculation, this is just going to be X long minus X naught or XO, and this will be 0.07 centimeters, oops, not centimeters, regular meters, minus 0.05 meters, and this is equal to 0.02 meters, and this is stretched length. Okay, and the last thing that we need to know is that the disc is 7 kilograms. So let's call that MD, D for disc, and that is 7 kilograms, kg. So these are all of our important things that we need to know. Okay, so the first question is asking us, what is the centripetal force on the disc? Now, the centripetal force is what causes the disc to stay in its circular path. If that centripetal force were to suddenly disappear, the disc would immediately stop following the circular path. It would just keep following the current direction that it was following. So, yeah, so the centripetal force in this case all comes from the spring. Okay, so I'll write that in a different color. F centripetal is equal to F spring. And we know this because, well, look, just looking at the diagram, there's nothing else that could really give us any forces. So nothing else to contribute to forces. Okay, now let's now that we know that the centripetal force is completely made up of the spring force, we just need to calculate the spring force. So we know the spring force, F spring, is equal to the Ks, the spring constant, multiplied by the distance or the change in distance of the spring, or the change in length of the spring from its original length. So that's why we had to get the delta x value. Delta means the change in x. So let's actually get this calculation real fast. Should be pretty straightforward. So we know that our spring constant is 147 Newton times meters, or Newton divided meters, my bad. And we had 0.02 meters on the like how far the change in length of the spring between its natural length and its stretched length. So we can run this calculation ASAP fast. 147 multiplied 0.02, and we get 2.94 newtons. And you can kind of see how the meters on the length neutralizes the meters in newtons per meter. So the units definitely work out, and we come to the same conclusion here. Awesome. Yeah, so the centripetal force is this 2.94 meters, because we know that the spring is who's supplying the centripetal force. And if we really wanted to, we could calculate how fast it's traveling, but the question didn't ask for it, so don't necessarily need to we don't need to calculate things that are not asked for us. It's typically not a great investment of time, especially on your tests where time can be quite tight. Okay, so this will be centripetal force. Centripetal force on disk. Okay, so the next part of the question is, what is the work done on the disk by the spring after an entire circle is done? Now, this is a situation where we want to bring up one of our important rules about work. Work has to have the force and the displacement be in the same direction. Or must be parallel. Only the parallel force and displacement components count or contribute to the work. So an example of me doing work is, or an example of work happening is if I drop something. Gravity is putting the force downwards and the displacement is downwards. Gravity is doing work in that scenario, but me pushing something perfectly horizontally, that's also work. That's work done from me because my force is putting it horizontally and it's moving horizontally, but gravity is not doing any work when I'm doing that, because gravity's force is completely downwards and its displacement is horizontal, so they're perpendicular, so there's no contribution of gravity on the work. In that situation of me pushing like a shopping cart, that's only going to be me doing the work. Gravity's doing no work because gravity is perpendicular to the motion. Now let's think about this situation real fast. Okay, so at any given point on the circular motion, given point along the circular motion, The centripetal force is perpendicular to velocity and its recent displacement and its displacement, I guess. Okay, so let's draw a circle real fast using Paint's beautiful tools. Okay, so suppose, let's do this in red. Yeah, a red circle, that's cool. And we can get a black pen. So at this moment right here, our velocity and displacement are this way, and our centripetal force is this way. They're perpendicular, no work. No work. Perpendicular. Okay, and on maybe right here, we have a similar story going on. So the FC is going towards the center, and the velocity is going this way. So we have another situation just like that. There's no work. The force and the velocity are perpendicular to each other, meaning the force and how it's moving in response to that force are perpendicular to each other. There cannot be any work done as a result of that, which means that the only possible thing here is that the work is 0 joules. Okay, so just remember to keep this in mind. I like to use that shopping cart example. Like when I'm pushing the shopping cart, gravity's doing no work. It's all me doing the work because gravity is going perpendicular to its motion. Okay, so that similar concept applies here, and we can see fairly clearly that there's going to be no work done because the perpendicularness. Okay, so yeah, the above solution is good. Mention of how the centripetal force is facilitated by the spring only would be good. Cool.